Powering our world, it takes some pretty incredible engineering, right? So in this explainer, we're going to take a journey from the industrial might of a coal plant all the way to the kind of elegant simplicity of solar power. We're going to see how the whole thing works. Okay, let's get into it.
Just stop and think for a second. The power for the screen you're looking at right now, where did it come from? It's so easy to just flip a switch and not think twice. But the story behind it, it's this wild mix of like pure brute force and some seriously brilliant physics.
Yeah, for a massive chunk of the planet, that journey starts in a place that looks just like this, a thermal power plant. And I know, this diagram looks, well, it looks super complicated. And you know what? It is. But don't worry, we're going to break it all down piece by piece, and we're going to start right at the beginning with the fuel.
So before you can generate even a single watt of power, you've got to get the fuel to the furnace. And this isn't a small task. We're talking about a massive, massive logistical operation that kicks off the second literal tons of coal show up at the plant's doorstep. And as you can see, it's not a simple process. There are a whole bunch of steps just to get the coal ready to burn. We won't get into every single one, but just look at that transfer stage. That part alone needs some seriously heavy-duty machinery to make it happen.
Okay, so to move all this stuff, plants rely on these enormous belt conveyors. You can think of them as the arteries of the whole operation. And get this, they can move up to 100 tons of coal every single hour. That's just a staggering amount of material.
But what about for shorter trips, or when you need to get around a tight corner? Well, for that, they switch over to more specialized gear, like these really powerful screw conveyors you see here.
And then, to get the coal moving up, like vertically into these huge storage hoppers, that's where bucket elevators come in. It's this incredible, huge mechanical ballet. And all of this is all just to get the fuel to the furnace door.
All right, so the fuel is finally in place. Now we get to go to the real heart of the plant, the steam generator. And trust me, this is where things get, well, kind of weird and really, really interesting. Because modern power plants, they can make steam without ever boiling water. How is that even possible? The secret sauce is something called supercritical pressure. So here's the deal. If you put water under insane pressure, we're talking over 220 times the normal air pressure around you, and then you heat it up, something wild happens. It enters this bizarre state where it's not really a liquid, but it's not really a gas either. It just transforms into this powerful fluid.
This diagram here kind of shows what's going on. See that dome shape in the middle? That's your normal boiling process, where liquid turns into gas, creating bubbles. But look at the red line. That's the supercritical process. By jacking up the pressure like crazy, the water completely bypasses that whole boiling phase. It just goes right around it. And that one principle led to a totally revolutionary design. So on the left, you've got a traditional boiler. It needs that big, heavy drum on top to separate the steam from the water. But on the right, that's the Benson boiler. And because it's running at supercritical pressures, there's no boiling, which means no bubbles, which means you don't need that giant separation drum at all.
And the advantages of this are just huge. I mean, ditching that massive drum makes the whole boiler lighter, smaller, and way safer. It can fire up in a fraction of the time, and it hits this incredible thermal efficiency, up to 90%. That's a real game changer.
But here's the thing. Even with a boiler that's 90% efficient, power plants are absolutely obsessed with squeezing out every last drop of energy. It's all about efficiency. To do that, they've got a few clever tricks up their sleeve to recycle waste heat. Let's check them out.
The whole philosophy is super simple. Any heat that escapes up that smokestack is just wasted energy, and frankly, wasted money. So engineers designed this whole series of accessories, basically heat exchangers, to grab that escaping energy and force it back to work inside the system.
Okay, so first up for the hot exhaust gases is a device called the economizer. Its only job is to preheat the water that's heading into the boiler. Think of it like giving the water a running start. Since it's already warmer, the boiler doesn't have to work as hard or use as much fuel to get it up to temperature.
Now the steam that comes out of the boiler, it's not quite perfect yet. It can still have these tiny little water droplets in it, and that's bad news. That wet steam can actually damage the turbine blades over time. So they send it through a superheater, which uses the furnace's intense heat to basically cook off those last few droplets. What you're left with is a pure, powerful, dry steam that's perfect for the turbine.
And there's one last trick, the air preheater. This is the final chance to grab some energy. Just before those exhaust gases finally escape up the chimney, their leftover heat is used to warm up the fresh air that's being sucked into the furnace for combustion. Why? Because hotter air means the fuel burns way more completely and efficiently.
And we're not talking about tiny gains here. This really puts it into perspective. Just look at the economizer. For every 6 degrees Celsius rise in the water temperature it causes, the whole boiler's efficiency goes up by 1%. Now, 1% might not sound like much, but when you're burning tons of fuel every hour, that adds up incredibly fast. It's a huge deal.
So that's the whole complex mechanical beast for getting heat out of fuel. It's pretty amazing. But there's a completely fundamentally different way to get the heat you need, and that's by just harnessing the power of the sun. When you boil it down, it's really a tale of two completely different approaches. On one side, you've got this immense mechanical force, a controlled explosion happening inside this intricate, powerful machinery. And on the other side, you've got the simple, silent capture of radiant energy from a star that's 93 million miles away. Now, to grab that solar heat, you could use a simple flat plate collector, like the one on the left. And those are awesome for, say, heating water for your house. But to actually generate electricity, you need way, way higher temperatures. And that's where concentrating collectors, like that parabolic trough on the right, really shine.
And this right here is the whole key. You use a big, curved mirror to focus all the sunlight hitting it onto one tiny little spot, the receiver. By doing that, you multiply the sun's energy, sometimes by 80 times. This intense concentration creates enough heat to boil a fluid, make steam, and spin a turbine, which, if you think about it, is the exact same end goal as the coal plant. It's just a totally different way of getting the heat to start with.
So there you have it, two incredibly different paths to the exact same goal. One is this massive mechanical beast, right? A true marvel of industrial engineering, perfected over more than a century. The other, it's like an elegant, silent trap for sunlight, just quietly turning radiant energy into the heat we need.
At the end of the day, both systems are designed to do one thing: turn heat into the electricity that runs our lives. So the really big question for all of us is, as we build our energy future, which model holds the key? Is it the complex, powerful machine, or the simple, elegant collector? Which one is going to define how we power our world?